Well, hello there, everybody. Let's learn today about Gauss's law. Okay, Gauss's law is just like a concept in physics that helps us find the electric field value at a certain point. Okay, before let's just recap what we learned before. Let's say we have a positive or any charge here. Like let's say this charge is Q. Okay, and this charge, we need to find the electric field value at a point P here, knowing that the distance between the charge and the point at which we need to find the electric field value is R. Okay? We found out using Coulomb's law and the electric field, we know that from Coulomb's law, F is equal to 9 times 10 to the power 9 Q1 Q2 over R square. We also found that the electric field is equal to F over Q. Then if we divide F over Q, we cancel, like if we have to find it this way, then electric field is equal to 9 times 10 to the power 9 Q1 Q2 divided by, let's say, Q1. Then Q1 with Q1 cancels out, and this Q2 becomes Q. So we end up with this. Electric field is equal to 9 times 10 to the power 9 Q over R square. Okay? There is R square here. I forgot to put it. Okay? So this is actually what the electric field is equal to for a point charge at a point P. So this is the distance between the point charge and a point P. Okay, so that's an easy way to find the electric field. Right? Gauss came with a more general concept to find the electric field for any charge distribution. So let's say we have a charge distribution like this, like a cloud. Okay, this is a charge distribution, and you were asked to find the electric field at this point. And this is the charge distribution. So this whole thing is Q. Okay, so where is R? So let's say this is R for this little part of the surface, and there is another, because this part of the surface is far away, and this part of the surface is even further far away. Okay, it gets really complicated. You need probably a computer to do this one. All right. How about if we have some uniform charge distribution like this one? Like this is a wire, and you want to find the electric field somewhere here. You cannot use this equation at all because this is for a point charge. But here we have a charge distribution that is cylindrical, or a charge distribution that is spherical. So it gets really complicated. But lucky for us, Gauss was able to help us find these electric fields for these charge distributions. Okay, for this algebra-based physics section, we are just going to focus on actually one charge distribution, which is a sphere, and we're going to have another example for a parallel plate capacitor. So we don't have to worry about too many charge distributions. We just have to worry about a couple of examples, and we will cover that here. Okay, all right. So before we learn about Gauss's law, we need to learn about something called flux. And I want to tell you a story, okay? Gauss is a very smart kid. He was a very brilliant kid. And he liked shortcuts a lot. He loved shortcuts. And one day at a school, he was sitting in his 9th grade, or I think, or 10th grade, and there was a lot of noise in the class, and the teacher was, maybe Friday afternoon, he just wants to go home, and so he gave all the kids, to quiet them down, a mathematical problem. He told all the kids to add the numbers 1 plus 2 plus 3 all the way plus 98 plus 99 plus 100. So he asked all the kids to find the addition of all of these numbers, and whoever finishes, they can go home. All right, so that's a good deal. So the kids quiet down. They got super, excited about this opportunity to go home. The teacher knew that a problem like that will take the kids about 2 hours to finish. But Gauss finished solving the problem in less than a minute. Can you think of a way what Gauss did? If you want to pause the video, please go ahead and do. And think how you can add those all numbers in less than a minute, okay? All right. If you pause the video and you're coming back, don't feel bad if you didn't know how to do it, because it's actually quite interesting. So Gauss came and added this number, 1 and 100, and that he said that's 101. And he added these two numbers. He said 2 plus 99 is 101. And he added these numbers, also 101, and so forth. He found out that he has to repeat this process 50 times. So he said, okay, 50 times 101, and he got the answer. Okay, can you believe that? That was Gauss, 9 years old. That's amazing. So let's talk about flux. Let's say you have a door, and there are 2 people coming through this door together. So the amount of people that are coming through this door, you can call it the flux of people. You can apply the same concept on what? On windows. So if you have a window and there is wind going through that window, the amount of wind going through that window, we can call it the flux of wind. Okay? So as I mentioned, if we have a window and we're talking about flux, and wind is going through that window, then the amount of wind going through that window, which is the surface area of the window, we can call it the flux. So the flux of this window, we can find it by simply multiplying the amount of wind times the surface area of the window itself. Okay? Now, what happens if we have this surface area like this, and through it there is an electric field going through? So the electric field is going to appear on the other side. Okay, all right. So the electric field, if we want to find the flux coming through that, this is the surface area A. So the electric field flux, I'm going to call it big phi. It's going just simply to be the electric field lines times the surface area. Just as simple as that, okay? This is the simplest form of the flux, okay? Now, before we accept this result, we need to understand many things. You may be asking yourself, what if, so let's say this is my surface area of my hand, okay? And the electric field lines are coming from the back of my hand and going through this. So I'm going to represent this pen as the electric field lines. So these are the electric field lines going this way, okay? What if the electric field lines were not going perpendicularly to the surface area? I mean by that, like they're going this way. Will you have more or less flux? What do you think? Or maybe I should tilt. Let's say the electric field line is going this way, and I'm tilting my hand like that. So the surface area is actually, when the electric field line comes this way, sees less surface area, right? Because the electric field line is coming this way, okay? If this was tilted, not like that, so the electric field line will see less surface area. What if I tilted it all the way like that? So basically the electric field line will pass by the surface area. It will not see it at all. It will see a line, but it's not going to count. So it seems that the bigger the surface area, the bigger the what? The flux. And that makes sense, okay? Now, if you understand that, that's good, because we need to move to the other side of this thing. Now, let's say I have this as a surface area, and there's the electric field lines coming this way, like this. I need to define something like to appreciate the surface area direction compared to the direction of what? The electric field lines. So to appreciate the direction of the surface area, they said, okay, what is this direction of the surface area? This is a surface area like that. Should I take it this way? 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 It is not unique. So they said, okay, maybe we should define the direction of the surface area to be perpendicular to the surface area itself. So if this is the surface area like that, the direction of it is perpendicular to it. Okay, remember that very well. This is known as the normal to the surface area. And I'm saying direction of surface area, I'm repeating that, direction of surface area. You may ask yourself a question, is surface area a vector quantity? And you bet, yes. Surface area is actually, area in general is a vector quantity. And the direction of the area is perpendicular to the area itself. That's how it's defined. All right? There is a reason for that. But we're not going to go into that now. But please try to convince yourself that the direction of the surface area is perpendicular to the surface area itself. Okay? And it makes a 90 degrees with the surface area. All right? That's the direction. That's a unique definition. So if there is an electric current, electric field coming this way, okay, in the same direction as the direction of the surface area, look, which means it's perpendicular to the surface area itself. So perpendicular to the surface area means parallel to the direction of the surface area. So what is the angle between this guy and this guy? Because they're parallel, the angle between them is 0. So basically, we have two options for flux so far. Maximum flux, so maximum flux is basically equals to the E times A, and minimum flux is equal to 0, because if the surface area was like that, the electric field lines will not see it. It will just go through it. Will go by it, not through it. Okay. And now we define that the surface area direction is this way, right? That's the surface area direction. And if we have an electric field line that's coming this way, so the angle is 0, and this is maximum flux. Okay. Maximum flux can be attained if we have a trigonometric function that defines the angle between the direction of the surface area and the direction of the electric field. This is 0, okay? So if this was 0, if cosine theta was 0, if theta was 0, then cosine 0 is what? 1. And that will retain this value, which is the maximum. Now, look, if I tilt my hand, this is the direction of the surface area. Tilt it like that. The electric field line is still coming this way. And if you look at the angle here, the angle, let me just fix it like this. You can see the angle between the direction of the surface area and the electric field lines is what? 90 degrees. If theta was 90 degrees, cosine 90 degrees is what? 0, and that's the minimum. And in between the maximum and the minimum, there is many values depending on what? Theta. All right? Let me explain that here. So I'm going to put this here. So let's say we have a surface area that is like a table, sitting like parallel to the ground. All right? So, and there is an electric field line coming this way, goes through the surface area and impinges outside from the other side. So this is the electric field. All right. Now the direction of this surface area is basically what? The normal to the surface area, as we said. So I'm going to call this n for normal. So this angle here, which is the angle between the electric field direction and the direction of the surface area, I'm going to call it theta. So if I want to generalize this equation for the flux, I can write, and I should write, that the flux is equal to EA cosine theta. Okay? So that's a primary equation for the flux. However, in Gauss's law, we may not have a nice surface like this one. Surfaces in Gauss's law could be any like that. It could be like, any kind of surface. All right? We have to be smart about our choices of surfaces, because theta will change. If theta will change, then we have to divide this surface into tiny little surfaces. Tiny. We can call each one of them A sub I. So the general equation for the flux is equal to E, the electric field, times the summation over I, AI cosine theta I, because the angle is going to change every time. Okay? But we will be more focused on this equation, but I want you to remember this one, especially when we talk about the parallel plate capacitor equation or problem. Okay? Okay, so now we agreed, if this is the surface area, this is the direction of the surface area, and if this is an electric field line, then the angle between the electric field line and the normal to the area is called theta, and the flux, which is phi or phi, is equal E A cosine theta. Okay? Now Gauss, where does Gauss fit in here? He came and he said the flux of an electric field is equal to Q enclosed divided by epsilon 0. And I will explain that in detail. Epsilon 0, you know what it is. It's the permittivity of free space, and it has a value. That will be given to you. Okay? Now, Q enclosed is the charge that is enclosed by a sphere. So it has to be enclosed by not a sphere or a surface. We call it a Gaussian surface. Whatever that is, okay, the charge has to be covered completely by the surface. If you look at the charge, you can't see the charge from any angle, because the charge is being covered by the surface. Okay, so the flux, that's Gauss's law. The flux is equal to Q enclosed divided by epsilon 0. So if I may write the flux, which is E summation over I for a generality, AI cosine theta I, okay, is equal to Q enclosed divided by epsilon 0. And this is a very important equation. This is known as Gauss's law. So now, if we have a charge, let's say we have a charge here, and I'm going to call this charge Q, and I'm asking you to use Gauss's law procedure to find, let's say this is a point here, point P, at a distance r away from the charge. I'm asking you to find the electric field using Gauss's law procedure at a point P, which is at a distance r from the charge or point charge Q. So what is the procedure to use Gauss's law? First of all, you surround the charge totally with a Gaussian surface that is appropriate for the charge distribution. What I mean by that, you look at the charge distribution. What is it? It's a point charge. If it's a point charge, your best bet for a Gaussian surface is a spherical surface. It's like a basketball. Okay? So you surround the charge completely with a sphere. So you surround the charge with a Gaussian surface, and for this charge it is best to have a Gaussian surface that is spherical, because that will minimize the amount of math we need to do. So Let's analyze the problem. We have to apply this equation. Since we have one surface, so this equation reduces to one surface, right? EA. We don't have any other surfaces. And the theta is 1 theta, and I'll show you why. So look here. Where is the direction of the surface here? The direction of the surface is what? That's the normal, right? Here. What is the direction of the surface here? It is like this. Normal. What is the direction of the surface here? It is like this. That's a normal. And in between, there's always what? You have millions of them, infinite number of them. So it's always normal to what? The surface itself. The direction of the surface is always normal to the surface itself, and it's always away like that. So look, if we have electric field lines coming out from this charge, it's going to be like this. In here, it's going to be what? We know that that's how the electric field lines go. And here, and here. So the electric field lines, every time you look at it, and the angle between the electric field lines and the normal is always what? Theta is equal to 0 here. Theta is equal to 0 here. Theta is equal to 0 here. So the choice of this spherical surface made it easier for us because theta is always 0 and cosine 0 is what? 1. Now we can apply Q enclosed. We have only one charge enclosed by that surface, so I'm going to call it Q, and epsilon 0 comes down. Now if I know that what is the area of a surface of a sphere? Remember, this is a sphere, this is not a disk. If that was a disk like that, then the surface area is equal basically pi r squared. But this is a sphere. What is the surface area of a sphere? The surface area of a sphere is equal to 4 pi r squared. It's good to memorize these things sometimes. They come handy. So E times the area of the sphere, which is 4 pi r squared, is equal to Q over epsilon 0. And if you rearrange that, because we are trying to find E, so divide by 4 pi r squared, divide by 4 pi r squared, you can find E is equal to Q over 4 pi r squared epsilon 0. Okay? And look, here's the magic here. So I'm going to say E, I'm going to rearrange this equation, 1 over 4 pi epsilon 0 times Q over r squared. Now, what is this equation? Do you remember seeing this equation? Yes, this is the equation for the electric field of a point charge at a distance r. So we just were able to find it using totally a different approach with Gauss's law. And this is amazing. Now you may say, oh my gosh, we went all through this hoop to find this, and we did all this Gauss's law thing and to put for a point charge. We found it from before. Yes, this is a point charge. What if the charge was a distribution of charges like this? Then you can't just find it using this equation. You have to apply Gauss's law. So there is where the power of the Gauss's law comes from. Okay, it can find the electric field of any charge distribution. If this charge distribution was like a line of charges, or maybe how about a plate like this, and its charge. How do you find the electric field for this one? You need to use Gauss's law. However, don't worry about this one or this one. We're not gonna use that. Okay, we're just gonna have now one more example, and we will be done with Gauss's law. And maybe more than one example. All right, thank you.